Hi, this is Miss Litton, and this is my wonderful Period 4 class. Say hi.
Hi.
All right, so we are starting in chapter 27 plus, and our guiding question for today is what evidence demonstrates that different species are related? And to do that, we're going to talk about, first of all, the history of our planet. And we are going to start here, and the universe is estimated, any guesses? Yes?
I'm 13 billion years old. Oh, way out.
Okay, 20 billion years old, potentially. And then our Earth maybe about 4.5 billion years old. There's some variations on that. But the first thing I want to talk about related to this is what I talked to you a little bit earlier about plate tectonics theory. And I want to see what you remember about that. So I would like you to sign in today. I'm going to remove some students first. As something fun you did over spring break that I could hear about. So if it was sleep, you can sign in as sleep. I don't know. Watch the fitness marshal, then you can sign in as that. Or yourselves. Yeah, however you want.
Wow, cool. Way to be
Disneyland. Somebody went to
Saw
a duck. Somebody did Dungeons. People still play Dungeons and Dragons?
Yeah.
Oh.
Wait, are we supposed to, as our name, who's it tell?
However you want to. Cry?
What?
Attacked by what? Who got attacked? What'd you get attacked by?
A duck.
Were you terrified? Okay, now this first thing I want you to kind of shout out back to me here is do it with your bio buddy. So just one of you, of the two of you, will contribute, or one of you can contribute to one and one to the other. And the first one, you can't see all of it, but it's what do you remember about the theory of plate tectonics? You don't look it up, don't look in your notes, don't Google it. Just, are there any key things you can remember about the plate tectonics theory? Talk about it with your bio buddy, put that up. And then listen, shh. Second shout out, I want you to tell me, how do you think it relates to biology? Don't celebrate your ignorance, be embarrassed, okay? How do you think it relates to biology? That will be your second box.
Annual states, mountains, one for each.
Just tell us what you do know, not what you don't know, okay? Just tell us what you do know, not what you don't know.
It shapes the way you think it thinks of it.
I see a lot of earthquakes, that's good, and moving volcanoes. Does anybody know, there's a good one. San something, does anybody know what it is? San Andreas. Yeah, good job. Good about Pangea, nice. Earth's crust is made out of plates and they are moving. Does anybody know what moves those plates on the Earth's crust? Starts with a C. Tell.
Conventional waves.
Convection currents. Yeah. All right.
Conventional oven.
There we go. The Earth is made of a bunch of different plates. When they move, earthquakes happen. Those are good. This shows the interaction between plates. Plates are sliding. So most of you have an idea. Oh, look, plates pushing together form a mountain range. That's a good one. We're talking about different kinds of plate boundaries. There's divergent, like spreading apart, and then coming together. Do you know what that would be called? Convergent. Good. And then transform plate boundary when they slide past one another. Good job.
Dinos.
Pangea separated the dinos. Okay.
John Malkovich owns 2 VHS.
Those are all good. Plates create earthquakes. Let's start looking at, I'm describing this first one. that I see. Plates affect the habitats of many organisms. Antarctica was not always down south in a cold area. It used to be very what? Hot, warm. So when you look at the fossils on Antarctica, you can find fossils of amphibians and reptiles. So that tells you that that whole land mass must have been somewhere closer to the equator where it was warmer. So that gives you evidence. But that also points to the idea that life can only exist where the environment isn't going to kill it, right? Where it's adapted to live. And so you don't have those reptiles or lizards in Antarctica now because it's too what? Cold. Yeah, exactly. Dinosaurs live. Very good. Okay, animals living on a fault. Yes. Plate movement can cause separation between species. That is a really good point. When the continents were together, what was one supercontinent called? Pangea. That's the one everybody goes to. That's not even the first supercontinent, okay? But it's the most recent one. And on Pangea, where the continents were joined, you might find a species of fern, which is on 3 or 4 different continents today that are separated by thousands of miles of ocean. So that tells you they once were all together, and now they've separated. And it gives you one of the pieces called biogeographic, that type of evidence for evolution. So you have, open trenches. Where would you find some trenches? Anybody know? Ocean? Have you heard of the phrase seafloor spreading? Yeah. Okay, so where lava is coming up and spreading them up, that would be at a divergent plate boundary. Okay, so several of you have a good idea about that. I'm going to show you a picture. Okay? And I'm going to highlight a few things, and I want you to look at the earth and what things they have labeled here and tell what you know. Look on here if you need some help. And just ping pong back and forth. Youngest bio buddy, and you can pick any one you want that I've highlighted. Just talk about it. And then oldest bio buddy, you pick another one and you talk till you've hit them all. Go ahead, go.
The mantle is different. Oceanic is denser, newer, and thinner, continental Convection currents are heat currents in the ocean magma that move across. And that's what makes the plates form as outer. Solid core is iron and nickel. Solid core. And it's like this.
Okay, let's add a little to our notes. So on Earth structure and age, parts of the Earth, the crust is a thin layer broken into plates where life is found. The ocean has thin, dense, and new relative to the continental, which are thicker, less dense, and older. Could oldest bio buddy explain to youngest bio buddy, why do you think the oceanic plates are newer and the continental plates are older? Why would that be? And if you want to look at actual timelines, it's coming up. Go ahead, just explain just that much. Why do you think that would be?
Because like there's some of the ocean
Okay, riddle me this. A motorcycle and a semi-truck are headed for each other. Okay? And they are going to converge. Who is going to win that battle? Semi-truck. Okay, is the semi-truck going to go under the motorcycle, or is the motorcycle going to go underneath the semi-truck? Motorcycle is going under the semi-truck, okay? So when you have oceanic plates and you have a convergent zone where they're meeting, you have the ocean plate and then you have the thicker continental plate, who's going to win? The continent, right? So the ocean plate's going to have to go under. Now, if it goes under and gets down there in the mantle and gets heated and melted, what's going to replace that part of the ocean floor that went under? What's going to replace it? lava coming from a divergent, right? Seafloor spreading. So new lava comes up and creates more of the oceanic floor, the part that goes under. So that's why your continents are newer, because all the mini battles between oceanic plates and continental plates, oceanic plates always lose and end up going underneath, and continental plates stay on top, and that's why they're older. Okay, check with BioBuddy and see, are you in the Shadowlands or Sunshine on that one? All right, then let's keep going. The mantle has molten minerals that set up convection currents below those plates. Now, right here at the top of the mantle is another word I wanted you to see. It's asthenosphere, the upper part of the mantle. And this is where rocks are in a semi-molten state. So that's right underneath the plates, or the asthenosphere. And when you look at the core is composed of what two things? Iron and nickel. How far away is the core from us right now? 4,000 miles beneath our feet. And it's solid due to intense pressure, though people are, guessing at the temperatures. When it says 7,000 to 12,000, nobody's 100% sure there, obviously. And why would the core have so much heat? The first one is heat from when the planet what? Was formed. The second one is frictional heating caused by denser core materials sinking to the center. So the denser one's falling, creating friction. And the third is heat from the decay of radioactive elements. Heat from the decay of radioactive elements. So let's talk about those radioactive elements that are in the core. There are two kinds of dating. When you want to age something, there's relative dating and absolute dating. Relative dating is when you can't find anybody to go to the prom with and you just ask your cousin. Absolute dating, you've been listening? Absolute dating, okay, is when you look at half-lives of unstable isotopes. For instance, if I found this rock let's say the rock was created, came out of a volcano and hardened. And let's say, maybe half of it almost was this, and this is an extreme, is an unstable isotope. And as it breaks down, it goes, for our purposes, white turns to what? Blue, as it breaks down, okay? But then I go and over time, this will break down. And if it breaks down, half of it breaks down, we would call that its what life? Half-life. And let's say that takes 5,700 years, okay? And then this would be its second half-life, which would be another 5,700 years. And this would be its third and fourth half-life. So scientists know how fast something breaks down. Sometimes it's in the thousands of years, sometimes it's in the millions of years, depending on the substance, sometimes it's in the billions of years for just one half-life. So if I find a rock, okay, and here if I find a rock and I dig it up out of the earth and it has this much of this isotope left, then I know about how old this rock is, because that would mean it had one half-life, right? This would be 2, and then 3 half-lives. Because this is how much, if it's first made, I would have, and I found it, this rock, where the percentage, the ratio was only this much. That's absolute dating. You know how fast an isotope breaks down and what percentage it should be, so you look to see how much is left, and then you can predict how old that rock is. That's absolute dating. And oldest BioBuddy, you're going to talk about it using this little chart right here. Go ahead, oldest BioBuddy. All right, and on your notes, that radioactive decay lifetimes and isotopic content in rocks provide a way of dating rock formations and thereby fixing the scale of geologic time. And so, I said there were two ways that you could do a half dating, absolute and relative dating. Relative dating is when you have layers of rock and you're assuming the layers on the bottom are older than the layers on the top are newer. So if you find a fossil in an upper layer, you're going to assume that that is a newer, right, species, and one that is in lower layers would be a older species. What do you have to look out for then, though? What kind of zones? Subduction zones, right? Because then it will take something that's newer and put it under, right? So you would have to look to see if that fossil is being found at a subduction zone. Youngest bio buddy, you explain the same thing about absolute dating using this picture.
Okay, so that's a newly formed crystal.
Look at the colors.
The green ones are the dark. The purple ones are the non-ones. And then
Okay, so we're going to expand what we kind of introduced a little bit ago. Why are the continental rocks older than 4 billion years old and rocks on the oceanic floor are less than 200 million years old? Well, we need to start talking about those convection currents. And so convection currents, why plates move. Heated material of the mantle rises due to the release of energy from radioactive decay of the Earth's core and expands, pushing old material aside and driving the plates apart. Apart at divergent boundaries. And then cooler, denser materials of the mantle fall. And I want to show you a short little video. Do me a favor, close your Chromebooks while we watch it.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental landmasses, the thinner of the two plates bends and slides under the other. As the edge of the seafloor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
Okay, tell your bio buddy what's one thing you either learned or reviewed from that. Learned or reviewed.
That once you get something goes underneath it, it takes the one of the
like too big the oceanic, because that's the one that goes under.
All right, so, not it. Whoever is not it, pass or play on telling your bio buddy a little bit about this picture. Go ahead. You should feel comfortable talking about this picture right here. Go ahead.
So you have the two ocean crust and then it's spreading in the center, which means that it's pulling apart. And then between the two continents, they're colliding. So the two tectonic plates are colliding, so then they're going to go like, since they're both continents, they're both the same thickness, so they're going to go up and down. And then, the ocean trench is when the continent and the ocean meet. And then
All right, now, whoever explained this, I want you to allow your other bio buddy to talk for a minute. Talk about what you think is going to happen at these three, and there are more than this, three different types of boundaries. Predict what will happen here. Go, other bio buddy.
Have you seen that episode of SpongeBob where he rubs the
What kind do we live on? Right, between the Pacific and the North American plate, right? So this is not any kind of subduction zone. We're not getting volcanoes. We're not melting any crusts here, but it can still cause problem as they try to slide past each other. So let's talk about all three at plate boundaries, and here's a little chart that can help you with that, okay? So on plate boundaries, what happens at the edges of plates? Divergent plates move away from one another. Move away from one another, as in seafloor spreading, where a new seafloor lithosphere is formed as magma rises. Now this is called a ridge push. Just like we saw in our little video, take a look up here for a minute. And we talked about those plates are moving faster than the magma underneath them, and that's because it's getting a push from that seafloor spreading, okay? And then the Earth's surface solidifies at a mid-ocean ridge. Convergent plates, they move towards one another, as in a subduction zone, and this is slab pull. So you saw in the video the subduction zone, if you have a continental plate meeting an oceanic plate, and the oceanic plate is going underneath, and as it falls, just like that necklace on that table, it's going to start to move and then speed up. It's pulling. So that's pulling those oceanic plates to go faster and pushing them to go faster than the magma and the convection current in the asthenosphere beneath them. So, okay, convergent. Okay, so oceanic and continental, if they meet, forms continental volcanic arcs, as in the Andes Mountains. If it's oceanic and oceanic at a convergent, it forms chains of islands, as in the Hawaiian Islands. And continental forms mountains like the Himalayas, which are always getting taller because these two continents are pushing against each other, and so it's forcing that upward rise. And then the third type is transform. Plates slide past one another. There's no destruction because there's no subduction, there's no melting. Now, we can have destruction, if it happens and we're living on the continent when it's sliding past one another. For instance, if you go to San Fernando Valley and you see the valleys, those valleys are created because the Pacific and the North American plate are traveling in opposite directions, and it's causing that buckling in the land. Now, what we would really ideally like is to have a bunch of little, what? Earthquakes to relieve the pressure, as opposed to one big one. That quick change is going to be devastating to California if it happened, right? Better to have a bunch of little earthquakes instead. Crust and upper mantle, however, there will be faults, which are breaks or cracks in the Earth's crust, along which movement has and will occur. For example, the San Andreas Fault. Yes?
Well, which one's the Great Rift Valley? Is that a conversion or is it divergent?
Look it up. Okay, not it. Whoever's not it, pass or play on 3 quiz questions over anything we've covered so far. Go. Not it.
Alright, you're first.
What's the difference between oceanic and continental and continental continental ocean and continental sea?
Where are you?
How is that water? Is that
Because I think when this goes over, it's like right here.
at least it's volcano versus mountain?
Which has mantles and
Let's look.
Yeah, where's convection currents?
All right, and go ahead and then close your books again, and we'll watch another video. There. Oh no, not it. Okay, look. You have to describe what's going on here. Whoever's not it, pass or play. Describe what's going on. What kind of boundary is it?
I'll play. It's going to be a volcano. What is it? Oceanic. Oceanic and continental. Okay, and it's going to go up. And then that's going to make it go up. And then
More things are
that's what
happening.
lava.
Oh, that's how it erupts.
Cool.
And then eventually that's going to fall off. And then eventually when it falls off, then that's going to be a volcano.
Oh my God! And it made a little volcano. All right. Sorry, we do have a video coming up. That's just not it. All right. So next, so plate tectonics theory. You have the basic definition, the study of the formation and movement of plates. The lithosphere is rigid, but is broken into movable plates that move a few centimeters a year due to the what currents? Convection currents in the asthenosphere beneath them. 15 major plate boundaries, not always easy to identify because they do not always follow continent or ocean boundaries. The largest plate is the Pacific plate. That's the one we're on. Yes.
May you repeat the lithosphere and the pieces
That move a few centimeters a year due to convection currents. Okay, and now we're going to watch a video that's very dramatic. So go ahead and close your books for a little bit.
Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and
This would
small
be early
land
Earth.
masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in.
Be careful. Be careful.
Bumpy ride.
It's gonna be a ride.
Here's how it might have happened. At first, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Arctica collided with what is now eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia.
Now, life is
After about
formed at this
300
point.
million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Well, apparently, the force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
Never know. It's very scary. Okay, tell your bio buddy, what's one thing you reviewed or learned? One thing you reviewed or learned.
That there was the light and it like light didn't wait.
All right. So you saw it in this video, but let's talk a little bit about now underneath the plate tectonic theory, some evidence about the plate tectonic theory. And what do you think this evidence is about? You're saying it. Volcanic, what do they call that? Ring of fire, yeah. So it's these areas where we have these volcanoes, and those volcanoes are going to indicate that there is a what kind of zone? Subduction zone, right? Because something's going underneath, another melting, and then coming back up. So your evidence, consistent patterns of earthquake locations. You can say, and volcanoes. Evidence of ocean floor spreading over time. And for that, your magnetic north-south, these have flipped a few times. Have you heard about this? Okay. And they can tell by the way it crystallizes in the lithosphere of the ocean that our magnetic north pole has reversed itself several different times. And in fact, it could reverse itself you know, that could happen within not too many generations of a lifetime. Can you imagine? It's not like a switch, like a toggle, like flip, now this is going to be north, flip, now this is going to be, it doesn't happen that fast. It happens over long periods of time, and that would obviously throw off all of our equipment that would depend on knowing north from south, right? Like what? What kind of things could that impact? Compass, what else? Something you fly in the sky. Airplanes, right? Okay, a lot of navigational issues could be impacted by that. So, evidence of ocean floor spreading over time given by tracking magnetic patterns in undersea rocks. And then looking at things like the warping in the San Fernando Valley, and also warping of land under loads such as the San Fernando Valley, and the bending under lakes and ice sheets. Lakes are heavy, ice sheets are heavy, and this causes that lithosphere to bend underneath that because it's just floating on those convection currents, right? And that too can be measured. And then that brings us to evidence for Pangea, which is a supercontinent. But what was the first supercontinent? Yeah. Okay. So supercontinent cycle. Supercontinents form and break apart over time, such as Pangea. So evidence for Pangea is the jigsaw puzzle, continental shorelines fitting together like a puzzle. So you can see that right here, how all the continents fit together. Okay, and then fossils. Matching fossils are found on different land masses, but these organisms could not have crossed the oceans. Like I said before, you could find a group, let's say, of fern, and it's found just like this where they would all fit together, and now that they're separated, you can just see little areas where had they been conjoined that you could see they had probably evolved there. You can see it with larger whole ribbons of fossils, both plant and animal. And 3, you have all of 3. Slate will take care of it. And then blue, you take care of 4, and the word you're looking for is Antarctica. Slate does 3, blue does 4, add in Antarctica. Go.
Mountain chains on the coastline of one continent continue on those of another across the ocean. So like
Ancient climates. It's evidence of a long phase underneath species in Antarctica, which is currently contained.
Evidence of war.
Evidence of warm climates and tropical species.
Okay, and then riddle me this. Have the plates stopped moving because now we have life on this planet? No. What do we know is going to continue to happen? They're going to continue to move. They will continue to move and then affect the life that grows on them. Yes?
Is there a change in the shoreline zone, like 200 years or something?
Well, do you remember how fast they were moving? How many centimeters it said in the movie? Yeah, maybe like 10 centimeters a year. So that's something that's measurable. Yeah, if you have a building on one of those, right, that could impact it, especially if they're going in 2 different directions. Okay. So continents are continually being shaped and reshaped by competing constructive and destructive geological processes. What would be an example of a constructive geological process? Making mountains and also seafloor spreading, right? Because you're making more seafloor where it's spreading. That would be examples of constructive. And then what would be examples of destructive geological processes? What kind of zone is that? Subduction zone. Good. And if plates continue to move at their current rate, scientists predict that in 250 million years, some new supercontinent will form. Yes, that is a long ways away. I agree.
Really? I think I might agree.
A little bit.
Okay, and then the last bit on the plate tectonics is about the coevolution of Earth systems and life. So this is showing you what trying to show you what the Earth looked like. What's a change you see as it spirals up? What's something you see happening in that spiral? Yes?
I see a lot less ocean, a lot more land.
Okay, a lot more land. What else do you see?
More life.
More life. What else? Does the color change at all?
Yeah.
What does it get?
Yellow.
Green. Okay, so the early Earth, which we're going to learn about here in our next section, the atmosphere in the early Earth, what they predict it to be, okay, is the same gases that come out of volcanoes. Does that make sense to you, talking about plate tectonics? Okay, and those early gases did not include any free oxygen. Are we dependent upon free oxygen now? Yeah. Okay, we have an oxidizing environment now. It's conducive, it breaks things down. If you leave something outside, it's going to break down, it's going to rust, it's going to corrode due to the oxygen. That's what oxygen does. It breaks things down. The early Earth environment was not oxidizing, it was reducing. So it wasn't about breaking things down. A reducing environment is more about what? Building. So due to that reducing environment, that created the ability for molecules to join together instead of breaking down, join together. So you could take those early gases dissolved into water and actually form some more organic molecules and the beginnings of life eventually. But once life started, at first that life would be anaerobic. Remember we learned about aerobic respiration and anaerobic. So first those organisms would be anaerobic, which means they don't need any what? Oxygen. But then, remember we learned about photosynthesis. When photosynthesis evolved, at first it was cyclic photophosphorylation, and then what else did we learn? Non-cyclic photophosphorylation. We said, remember water, 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 water. What are we going to do? Break it in half. What do we get? Oxygen and electrons. The oxygen started. When non-cyclic photophosphorylation came about, all of a sudden there's oxygen in the air. So now organisms could go from being anaerobic to what? Aerobic. Now that they have more oxygen, they make some, a lot of it, right? So think this process out. If you can make more ATP, then you can support, instead of being smaller life, you can be bigger life. So due to that, you could have multicellular organisms. And you could go from being small algae to a bigger plant. Now, what anchors a plant? Roots. Roots grow into the rock or the soil, or first lichens maybe, into the rock, and break it down, and then they die and they create more soil. And then some other plants can grow a little bit deeper because it's broken down a little bit more and there's more soil. So instead of being small plants, over time you could become bigger plants. So the life is changing their environment that they're living in. The life is changing it from rock into soil. The life is changing the reducing environment into an oxidizing environment. And as a result of being an oxidizing environment, that affects the life you can have. So the Earth's environment impacted the ability to make life, and then life impacts the Earth's environment, and then the Earth's environment impacts life. That's why we can see that kind of feedback system between the two. So on your notes, go where it says system interactions and feedback. Geoscience factors control the evolution of life. So if you look at the geology, you want to know, is there water? Are there nutrients? Is there any oxygen in that environment? And then life continuously alters the Earth's surface. Life continually alters the Earth's surface. And let's look at some examples. Oxygen in the Earth, photosynthetic life generated what gas? You tell me, you know the answer to this. Photosynthetic, what? Oxygen, good, put oxygen in there. Oxygen allowed for multicellular organisms to evolve and also caused the weathering of rocks. Life on land and weathering increased the formation of soil. Soil allowed for the evolution of land plants, which then increased the oxygen even more, etc. Second example, coral reefs. Polyps build coral reefs from calcium carbonate, which then provide, do you know what you call where an organism lives? It starts with an H, not home, but it's habitats. Good. Niche is what it does, okay? So calcium carbonate, which then provide habitats for the evolution of new life forms. Not it? 3 quiz questions on anything we've talked about up to this point. Go.
What is this called?
And we'll pick this up in our next
We both
presentation.
What is this?